Good morning, ladies and gentlemen. Nice to see you again. So we start the first problem solving session of this course. As you know, we will engage in many activities during this session. And one of the activities are instructor presentations. So what we will have today are 4 relatively short instructor presentations. What about? We just had a lecture, refreshing of our quantum knowledge, all right? But that has been done at some theoretical level. Now we want to get it a little bit more practical for you to recall how to write formulas, how to compute different things, and simultaneously give a little bit more details about the topic of the lecture, like perturbation theory, like Heisenberg equation, like qubits, or density metrics. That will come in a row, but it will be much more technical than usual lecture. Good. You're supposed to react because it's just not for us, it's for you. So if you have a difficulty, if you don't understand something, please do not hesitate to ask. Better to put it into the chat. But yeah, if your question is not answered, please speak up. Very good, sir. If there are no questions, I would give the word to Miriam. She will talk first. Is there any homework out already? Yes, Yanis, I have already mentioned that homework usually comes when you're supposed to have enough knowledge to start homework. So homework for the first package will be released after third lecture. So it will be yet in 10 days or so. Other slides available for this session. I'm not sure about the slides. There will be video of this session. I guess it will be easier. Could perturbation theory be repeated in more detail? Maybe. Surely, we are aware of such requests. We will repeat it soon. After Miriam, there will be Riester, hopefully, and well, everything will be fine. Are there many more questions? No, not really. So, Miriam, why don't you begin?
Thank you very much, Yuli. Good morning, everyone. My name is Miriam Blauboer. I am a staff member in the Department of Quantum Nanoscience, and also together with Yuli and Christo and Max, an instructor for this course. So we will meet many times this semester. I have a little refreshing part for you this morning about essentially 2 topics: representation of a wave function and how to calculate eigenvectors. I prepared a few slides, so let me share my screen so that we can all see it. So most of this has already been mentioned in the first lecture that you heard from Yuli last Thursday. It relates to chapter 1.3 in the book, where operators are introduced and also representation of wave functions and operators. So I'll just try to go through it once more and maybe explain a little bit a few things that are not in the book, but very much related to this. If you have questions, as Yuli said, please ask. If I go too fast or too slow, please also say so, and then we'll see how it goes. So very basically, I'm sure everyone has learned this in their undergraduate courses. information of a quantum state is contained in a wave function. That's almost one of the first things that you learn when you start learning quantum mechanics. Those of you who learned from the book by Griffiths, well, he starts with this in the first chapter. So information of the state is contained in something we call the wave function. Psi is the usual symbol, and here it depends on spatial coordinate, vector r and t. Physical quantities are represented by Hermitian operators. For example, A here. And each operator has eigenvalues and eigenfunctions. This was also in the first lecture, the refreshing lecture. And the Schrodinger equation's stationary form then says that an operator acting on a wave function psi equals the eigenvalue, here it's called A0 times psi. So nothing new so far, I hope. The expectation value of an operator is then given by this expression, which is an integral over all space. Oh, this should have been a vector r, and then it's psi star a times psi, where psi star is the Hermitian conjugate of the wave function psi. So all this is the basis of operators and their eigenvalues and eigenfunctions. And here this wave function is an actual function of space and time. And then someone called Dirac came, Paul Dirac. Julie talked about him on Thursday. And he said, well, this notion, this wave function, this spatially dependent wave function is a little bit restrictive, too restrictive. He said it's more convenient to think in a more abstract mathematical way about wave functions and operators, where you regard the wave function not as a function of space and time, but rather as a vector that lives in a vector space called the Hilbert space. And this is a multidimensional linear vector space. So Dirac said, let's represent the wave function as a vector, which is an element of a vector space, a Hilbert space, and this vector space has a basis. And let's write it down in a slightly different way, more compact, as this ket of psi, which you also know very well. Operators, in the same way, then become matrices. Matrices also in the same Hilbert space, expressed in the same basis. So instead of this equation here that we started out with, this eigenvalue equation, we would write it in Dirac notation in the following way. Now there's the operator has been changed to H, the Hamiltonian, but it doesn't matter. It's still the eigenvalue equation. H acting on wave function psi, which is now written in Dirac notation, equals corresponding eigenvalue, which for the Hamiltonian is the energy times the wave function. And the expectation value in more general Dirac notation is then given by this inner product of psi and H psi. Now this Dirac formulation leads in a very natural way to the notion of representation, which is the second topic I would like to say a few words about. So representation of wave functions and operators. The key point here is that if you think about a wave function as a vector in a Hilbert space, which has a basis, then the wave function can be represented in many ways. And last Thursday, Julie had this nice picture where he drew three axes, x-axis, y-axis, and z-axis, and the wave function was a vector in this space, the basis can be chosen in many ways. So the representation of this vector, the wave function in that space, is not unique. It depends on which basis you choose. And what does representation then mean? Well, by representation, we just mean the projection of this vector on the basis vectors. And you know that if you choose a different basis, In generally, that will give you a different projection. But the physical entity, the wave function, the vector, will still be the same. So each wave function can be represented in different ways. And this projection of the basis vectors, that is expressed as follows. Also a well-known expression, I can write any wave function psi as a sum over coefficients and projections on the corresponding wave functions, on the corresponding basis vectors, which are here the eigenfunctions of the Hamiltonian n. There are some well-known representations that we also learn about in our bachelor courses. Two of them are the R representation and the P representation. R is the one we saw on the first slide, psi of R, and that is the representation in R in actual space that is always used when you work in the Schrodinger picture. There's also the P representation, where as a basis, you choose a basis of plane waves. The notation for these plane waves in Dirac notation is P here. And then my wave function, the same wave function as this one, will be written as a sum of coefficients times these P basis vectors. So you have a choice and you choose in each problem the basis that is most convenient for that particular problem, knowing that it will not alter the physics, because always you're talking about the same wave function and the same physical quantities as operators, which are simply written mathematically in a different way, depending on the basis. Talking about matrices, we come to the last topic for my small session here, and that is how to calculate eigenvectors. It's just going to be a brief reminder, because I'm sure everyone, of course, learned this in linear algebra, but still it can be good to refresh things. What we see in the homework, because there are also homework problems where you have to find eigenvectors, we often see that most of you find it very easy to find eigenvalues, to calculate them, but a little bit more difficult to calculate the corresponding eigenvectors. So I'll just go over the procedure, how to find eigenvectors, and leave you with a little exercise to do later today, perhaps, just to practice, to refresh how to actually calculate eigenvectors in practice. So let's consider a matrix M, capital M, and let's say that it's n by n. Let's also assume that we already know the eigenvalues. You know the determinant method, you calculate the eigenvalues. I'm going to assume that everyone manages to do this. So n by n will have n eigenvalues, and let's call them lambda 1 to lambda n. Now, how do we find the eigenvector corresponding to each of these eigenvalues? For that, you have to solve this matrix equation. For each eigenvalue that you found, solve the matrix equation, which is this thing here. It's the matrix M, and then subtract it from it the eigenvalue times I, and I is the identity matrix. So M minus lambda I times the eigenvector Vi that we're trying to find must be equal to 0. And this is vector 0, a column with small n zeros. So this is the matrix equation we have to solve to find this Vi. How do you do this? Well, the formal technique for this is by Gaussian elimination. I think it's called in English also. This I'm not going to explain. If you don't remember how to do it, please look it up again. It's nothing, it's just a technique for solving this coupled set of equations. What it comes down to, the essence of the technique, is that this big matrix equation gives you n minus 1 linearly independent equations. And since you have n unknowns, and this only gives you n minus 1 equations, you need another one, and luckily there is one. That's the normalization condition for Vi. Every eigenvector must be normalized, so the normalization condition gives you another equation. And then all you have to do is solve these equations. You have n equations for n variables vi, and that gives you a solution for each of the entries in this, each of the elements of this vector vi. Try to apply this yourself to the 2x2 matrix that was mentioned in the first lecture. It's on slide 14 of Yuli's slides. They're already on Brightspace. You can easily find them. Yuli talked about the qubit, and there was a 2x2 matrix describing this qubit here. Try just for yourself to calculate the eigenvalues. I think they are given on the slide, so that's easy. But try to calculate the eigenvectors corresponding to the two eigenvalues of this qubit. And then check that they actually do form a basis, these eigenvectors, and also check that they are properly normalized. And if all of that is true, you have found the proper eigenvectors. It's very important because we will use it. I already said it's coming back in the homework. You will encounter this in the course later on. All right, that was everything I wanted to mention on operators, representation, and how to find eigenvectors. Are there any questions? Let me see if I can actually see the chat. Max is asking, since nobody is asking, what about degenerate eigenvalues? Well, for degenerate eigenvalues, procedure is actually a little bit different. Let's see, you first have to calculate, if you assume again that you have already found the eigenvalues and some of them are degenerate, then there is, the method is also a matrix elimination method where you have to find the eigenvalues, but it's slightly, you can, let's say if you have the book by Griffiths, look at chapter 6, because Griffiths explains very well, step by step, how you calculate the eigenvectors of a degenerate matrix. I don't have any slide on it for you right now, but it's in chapter 6 of the book by Griffiths. Any other question? Sasha is asking, you mentioned that the Dirac viewed operators as matrices. That's true. Huh? He suggested to represent operators as matrices. He couldn't do that with infinite dimensional Hilbert spaces. Why not just keep the operators as operators? Well, they are still operators, but if you have to do calculations, it's very convenient to work with matrices and vectors. And this is also true for Hilbert spaces of any dimension. So this Dirac technique always works. And in some other cases, it might be more convenient to simply use the abstract notation, the operator A acting on the ket psi. That also is sometimes convenient. Yuli will talk about that in one of the future lectures when we talk about creation and annihilation operators. So both ways to calculate eigenvectors and eigenfunctions are useful. How could one represent the P operator as a matrix? Wait a little bit, it will come. Yeah, it's not yet been discussed in the book. Again, the book by Griffiths, if you have it, has an explicit example how to do this. I think it's in, I have to think, either chapter 1 or chapter 2 there. So you can also do this, writing it in a basis of plane waves. If there are no more questions, then I will hand the floor to Risto who will continue this refreshing session.
Thank you, Miriam.
Ah, no, sorry, Max, sorry.
No problem, thanks. My name is Maximilian Russ, and I'm a postdoc in experimental group, but I'm also a theorist in QTech. And I give you, I'm also one of your teaching assistants. And today I tell you a bit about Schrodinger picture, which was already mentioned by Miriam, and also about the Heisenberg picture, which sometimes is more convenient. So I have prepared some slides. Okay, so the content of my little presentation, I go first into the Schrodinger picture, give a quick refresher. Then I go into the Heisenberg picture and tell you about its properties and how to derive it. And then I go slowly over two exercises. First is the Zeeman effect, and the second is the harmonic oscillator, where we actually learn what, or where we actually apply what we have learned during these first two little chapters. So the Schrodinger picture is most commonly used picture. In the Schrodinger picture, the state vectors are always time dependent. This means you have the famous Schrodinger equation given here in the representation already introduced by Miriam, which is the Dirac notation, that you have the time derivative of your wave function or state vector, which is equal to minus I divided by h bar times your Hamiltonian, which in this case is a matrix representing in this Hilbert space, which is applied to your state vector. And if your Hamiltonian is time independent, what you can get, or you can solve this differential equation very simply by exponentiating this Hamiltonian operator, and you get the solution that your final wave function as a function of time, psi of t, is given by the matrix exponential of minus I divided by h bar times your Hamiltonian times your initial state at time t equal 0. At the same time, in the Schrodinger pictures, the operators are also time independent. And now let's look what happens about expectation values. So we just do a little math. So in this line, I calculated the time evolution of an expectation value. So the expectation value is given in this Dirac notation as a bracket or a sandwich where your operator is between your two state vectors psi of t. And if you want to know the differential equations for this expectation value, you take the derivative of this complete sandwich here. And now you use the product rule, because we know that the operators is time independent and only the state vector is time dependent. We can use the product rule to give these two terms here, where we first have to differentiate the first state vector, and then we still have the second part. And we also do it vice versa, where we take the derivative of the second state vector. Now, if we do the math, we find very conveniently from this first equation here that this is only giving us the Hamiltonian back in our equation, and we can also rewrite this back as the commutator of the Hamilton operator with your operator you want to know more about. And now you have an equation which is given in this form here, that you have the derivative of your expectation value is given by I times the expectation value of your of the commutator of the Hamiltonian operator with A. In the Heisenberg picture, we use this knowledge a bit. We transform now into another picture or a basis in a set of basis states with which have the following requirements. So now we want to have that our state vectors are constant in time, so they do not depend in any form in time, but on the contrast, what we want is that the operators itself now involve in time. And we have here again the solutions for the time evolution for the time-independent Hamiltonian in the Schrodinger picture, depicted here by this matrix exponential. And we again want to use these expressions for the expectation values. So the expectation value itself is given again by this sandwiched A operator. But now we can, because we have this relationship here from the solution for our time evolution, we can now rewrite this expression here in terms of pulling out the time dependence in form of this matrix exponential from both sides. And now we redefine this middle product here as our new operator H A in the Heisenberg picture, which is denoted by this subindex H. And in this, and now we directly find that our operators in the Heisenberg picture are given by the multiplication from both sides of this matrix exponential of your operator in the Schrodinger picture, which is time independent. And the nice thing about this is that now the state vectors in the Heisenberg picture become now time independent, because we only use the initial state in this redefinition. So we have now our new operators in state vectors defined as follows. And now we want to know what happens with the time evolution of the operators, because for the Schrodinger picture, we have the classical Schrodinger equation, which gives us a time evolution for the state vectors or the wave functions. It's now a little bit different for the Heisenberg picture, because here our state vectors are now time independent, but our operators evolve in time. So therefore, it's only natural that we form now a new equation of motion for the state vectors directly. And yeah, we just do the math. So when we want to take the derivative of a operator in the Heisenberg picture, we know from this definition here that we have to apply the product rule, and we get two terms. In the first term, we take the derivative of only the first expression of the first exponential without the minus sign. And in the second term, we apply the derivative on the second term. And I see here there's a minus sign missing. And when we do the math, so here still assuming that your H is time independent, if you now get the if you now apply the derivative to the matrix exponential, you just get the I times the Hamilton operators down, and the same on the right side, just with a minus sign. And now you can directly see that here we have again our Heisenberg operators, these two terms here, and we can regroup them, and we directly find that that this expression here is the commutator of your Hamilton operator with your Heisenberg operator. Therefore, the new equations of motions for in the Heisenberg picture for operators is given by d to dt of your Heisenberg operator is given by I divided by h bar, and the commutator between your Hamilton operator with your Heisenberg operator. Some of you might find this looks similar to the classical picture in the with the canonical canonical transformation, and this is indeed the case. So let me now summarize the two pictures. Here on this, here on the left, you see how the dynamics of a quantum state or an operator is depicted in each of these pictures. For the Schrodinger picture, we have the equations of motions for the state vectors or wave functions, while in the Heisenberg picture, we have an equation of motions for our operators itself. And these are the requirements. And now you might ask, is there also a hybrid form? Yes, there is, and this is called the interaction picture, which also has some advantages. But here now the state vectors evolve in time and the operators evolve in time. But I will not go into much detail about the interaction picture. You will find it in you find it also in the book by Yuli Nazarov. So now we go to the exercise 1, which is a spin in a magnetic field. And here I go extra slowly through, so you can all directly follow what I'm doing in each line. So please directly write in the chat if I'm too fast for you. So the interaction between a spin of some particle and external or any magnetic field B, which we now say is pointing towards the Z direction, is given in general by this Hamiltonian. Here G is the chief vector of your particle, mu Bohr is the Bohr magneton, and B is the vector B and times S, and S is your spin operator, and this is here the scalar product. And the vector of a spin operator is just a vector which has in each component the X, Y, and Z components of your spin operator. But since we now have chosen a magnetic field only in Z direction, we can directly apply our scalar product and find that that our Hamiltonian gets simplified to G mu Bohr B times only the Z component of your spin operator. And now we define these three terms here before as H bar omega. And now we are interested in the time evolution of the spin operators as X, as Y, and as Z, which are the components of your S vector. So which equations do we want to use for this? And the solution for this, we use the Heisenberg equations of motions, because previously I told you that with the Schrodinger equation, you get the time evolution of your states. But here we are now explicitly we want to find the time evolution of the spin vectors, spin operators itself. So the Heisenberg equation of motion for the x component is given by, as we learned previously, by the commutator of your operator h with your x component of the spin operator. Now, if we do the math, we find that this can be simplified, and our Hamiltonian is given just by h bar omega cz. The h bar cancels out, and we have only I omega and the commutator between sz and sx. And here we just use our definitions of the spin operator commutator relationship and find that this is minus I s the y component of the spin operators, and then we can simplify this by taking I squared equal -1, and we find that the derivative of the this x part of the spin operator is given by omega times the y part of the spin operator. We can do the same math also for the y component, and we find very similar steps. It's just here that we now get a different commutation relationship, where we, instead of a plus sign, a minus sign, we get the plus sign, and we end up that the derivative of the y part of our spin operator is minus omega times the x part of your spin operators. And in the last step, we also want to know what is the dynamics of the z component. And the z component has a very simple relationship, which is that it is time independent, because we know that every time we have if we have a commutator between the same operators, we know that it is 0. Therefore, the time derivative of the z component is equal to 0. Here I have rewritten the Heisenberg equations as a vector equations, but it's essentially directly the same as before. And when we now put in the x into the y component, or the y component in the x component, basically taking another derivative of it, we directly find for both the x and y component of the spin operator that the second derivative d squared divided by dt squared of the same operator is given by minus omega squared of the same operator. So we don't have any cross relationship between different operators. So with this comma notation, I spared myself one line of writing. And this differential equations looks very similar. All of you should be able to solve these kind of differential equations, and the general solution is given by a superposition of cosine wave function and of operator times the cosine of omega t plus another operator times the sine of omega t. You can do the math itself. Again, if you take the derivative of the twice the derivative of the cosine, you end up at the cosine again, and for the sinus as well. Now we force ourselves some boundary conditions or initial conditions at time equals 0. We say that the spin operator at time equals 0 is given, which is this axy component, is given by h bar divided by sigma xy, where sigma here are the 2 by 2 Pauli matrices. If you have
Max, there are some questions in the
yes.
chat.
Yes, sorry, it's not highlighting. Yep, thanks. How can I find the chat here? I'm sorry. Ah. Yeah. So I start from the beginning. The first question is with the last step. Do you mean this step here? Perfect, thanks. Yes, so in this equation here, what I took the x component, so it's better seen. Maybe I've gone too fast for it. For this step, what I've taken is, we know the relationship between the time derivative of the x component and the y component, but now we can also put in, or we take another derivative in front of it. We take the double derivative of the first line here, then we get still the derivative of the sy operator here, where we now put in the second line. And we can, the advantage of this is we get back our original operator. So with 1 in 2 or 2 in 1, I meant you take these equations and put it into this equation in this first line equation here. Okay, seems to be clear. And with x and y, I exactly as in the chat mentioned, these are two equations. It's just my laziness that I wrote here. Only one x comma y means the equation holds for x and also for y at the same time. But I keep in mind to not use these notation too often anymore. Okay, there's. Okay, the notation, what I mean here is that this equation once holds only for x. So just delete the y term, and the same equation also holds for y. Is this now clear? Thanks. And yeah, I think these are all questions. If not, please, yeah, do not hesitate to ask. Then let's restart. So the boundary conditions we force ourselves on at t equals 0 are that our spin operators are represented at time equals 0 by the Pauli matrices. This means we look only on a spin 1/2 particle where we have either the up or the down state. And from our Heisenberg equations of motions, we also directly have now the relationship towards the derivative of the x and y components at time equals 0, which are given by the omega bx components. And we find that the derivative of our x operator at time equals 0 is given by h bar omega half sigma y. And on the other hand, the derivative of our y operator at time equals 0 is given by minus h bar omega divided by 2 sigma x operator. Oh, yeah, I see there are some mistakes in this. So first, this is a vector. And thanks for pointing out this. And what I've taken here is each component. So I'm taking the this notation on the top is only each of these 3 equations written in a single equation. So the first line here is only about the x component, which is I'm sorry. Yeah, I see now the problem. Ignore this equation of motions. I'm sorry for that. Yeah, exactly. It should be a vector as y, as x, as z. Yes, yeah, exactly right. Thanks for pointing this out. Let's move. So we can find now for the explicit solutions of the Heisenberg equations of motion, we find for the x component, we have now the time, the x component of our spin operator is given by h bar divided by 2, the Pauli x matrix times the cosine of omega t plus the Pauli y matrix times the sine of omega 2. We find for the y component of t, we find that it's h bar divided by 2. And here we have a sigma y component as at time equals 0 and a minus sigma x component minus for the sine term. And the z term is equal 0. It's just constant sigma z. Now it's get a little bit more into it. We now want to force thanks, Sasha. That's actually nice. Yes. I look into, and they give you in the next, I give you an update about this. You're right, you can get it with a cross product, but you need to make, yes, yeah. Yeah, so we now have a prepared initial state, and with this cat with up arrow, I mean that we have our spin starting in which is defined as the spin up state, and with an arrow pointing down, this means your spin is pointing in the downwards direction. And now what I have here is a spin up plus a spin down state. And this state here is actually a spin state pointing into the XY plane. So it's on, it's a horizontal spin direction. And now we want to know what is the time evolution if we have this prepared initial state here. And we find directly that we get this by again taking our operators here. We now have our time dependent. We have now our time dependent operators. But now the nice thing in the Heisenberg picture is we don't need to solve another equation. We can just take the sandwich of our spin operator and sandwich it between our now initial state and see what is the time evolution directly. We don't have to solve the Schrodinger equation again to get the time evolution for each initial state. And you can do the math yourself. It's not very complicated. But what you find directly is that the time evolution of this initial state here, the expectation value, is given by a cosine of omega t, a minus sine of omega t, and 0. And this resembles a precession around the z-axis. This means that if we start a spin on the horizontal plane, we get directly a rotation around around the z-axis. Lucas, do you mean this last step here, from here to here? Yeah. I haven't prepared it on slides, but what you do is you write directly your spin up plus spin down. And then you have your operator. I just do it example for the first line. And you have two of them. You have here up plus a down. This operator here is given by sine of omega t. And now we have to write these states into a matrix representation. So we typically choose here the convention that a up vector is given by a 1, 0, and a down vector is given by a 0, 1 vector. And the Pauli matrices itself are given by sigma x equal 0, 1, 1, 0, and the sigma y is given by 0 minus I, 0. And now you only need to do a matrix multiplication. Exactly. we write it into one basis, and then we perform the computation. There's also example in of these kinds you can find in the book of Yuli Nazarov, if I'm not mistaken, or it's one of the exercises. Okay. So this means the spin rotates around the z-axis. Are there more questions? There's a H bar missing, yes.
Yes, that's what I wanted to suggest. Max, first of all, what else would you like to talk about? About harmonic oscillator or Heisenberg equation?
Exactly.
Okay, let's have 7 minutes break till 9:50. And then we will finish the presentation. And
okay, thanks.
all right, we are back.
I'm quickly looking again to find the chat. Okay, thanks. The second exercise is about the harmonic oscillator. And the harmonic oscillator describes a particle in the quadratic or harmonic potential and is depicted by the following Hamiltonian. So we have the p squared divided by 2m, which represents the kinetic energy. And we have the 1/2 m omega squared x squared, which depicts the potential energy. And we have also the commutation, the canonical commutation relationship between our x and our position and momentum operator, which is given by IH bar. We use this later in several places, so keep this in mind. Now we want to find the time evolution of the position and the momentum operators in using the Heisenberg equations of motions. And we directly use the equations of motions for the x operator. So the derivative of the x operator is given by I divided by h bar with the commutation relationship. And now we can directly place in our Hamiltonian. And here I already simplified that x commutes with a function of itself. So x, the operator x commutes with x squared. And we go further and use a commutator rule. I'm not sure if you learned it, but if so, you can do, if not, you can do the math very easily, just writing these terms here out. And you'll find that you can pull out, if you have a squared here, you can either pull out, you have to pull out the p once in front and once afterwards. And now you can put in directly the commutation relationship. Note that here the commutator is flipped, so we add a -1, but the -1 here is negated by the I squared term. And in the end, what we find is that the derivative of the position operator is given by the momentum operator divided by the mass. Which makes totally sense if you think it in a classical sense, that that the momentum is given by the mass times the derivative of the position, which is equivalent to the speed. Now, the second, now we want to find our equations of motions for the momentum operator. And here we have to do exactly the same, but instead of taking the commutator with Hamiltonian and x, we take it now with the momentum operator. And we plug in, I already skipped the term with p because p squared and your momentum squared and momentum commutes. And we directly find the following form. We have x squared, the commutator between x squared and p with some constants in front. And we can do the same trick as above. We expand the commutator. And we find here directly now our commutation relationship, and we find that the derivative of the momentum operator is given by minus omega squared m, your position operator. And now we do exactly the same trick as for the spin in the previous exercise. We plug now 2 in 1 and 1 in 2 and taking the double derivative, and we find again for both cases that the second derivative of the position operator is given by minus omega squared the position operator. And we also find that the second derivative of the momentum operator is given by minus omega squared by the momentum operator. So we have now these two Heisenberg equations of motions, these second order derivatives. We also know from the previous setup already the solution, which are depicted here. We have we use the general solution that our position operator is given by some matrix AX cosine omega t plus bx sine of omega t. And we have the momentum operator, which is given by some matrix AP cosine omega t plus BP sine omega t. And now we enforce again thanks, Janice. Yes, I tried to do that actually with PowerPoint in if there was some die, but yeah, maybe I should enforce it with 1 and 2. Thanks for this advice. I keep it in mind. And we enforce some boundary conditions at time equals 0 that we start at a position x0, and we also start with a certain momentum at time 0. We just depict them as x0 and p0. And again, from our differential equations, we also get that the derivative at time equals 0 is the momentum at time equals 0 divided by the mass. And we find that the derivative of the momentum is given by minus omega squared m times the position. And this here, I'm pretty sure it becomes very simple to visualize. Now, at the next step, we want to find the explicit solution by setting these boundary conditions we already found into action. And we find that our x operator, our position operator, is given by x0 times cosine omega t plus the momentum the p0 divided by omega m times sine of omega t, and p, the momentum as a function of time, is given as p0 cosine of omega t minus omega m x0 sine of omega t. And now here you can directly see a very nice correspondence between these Heisenberg equations of motions and the classical harmonic oscillator, where you also have that the position switches between 2 points, and that the derivative, that the speed also, when you are at max position, you have speed 0, and vice versa. If you're at a 0 position, you have max speed, and the momentum is exactly depicting that. So we have found that the Heisenberg's equations of motions with this exercise, that they have very often a classical correspondence and can be visualized in a nice way. So with this, I want to give you some take-home messages. We first have the Schrodinger picture, where the time evolution is given as a function of the state vector and represented by the Schrodinger equation of motion. And our equation of motion is for the state vectors or the wave functions. And here the dynamics is described by the concept of a wave function, while in the Heisenberg picture, we have equations of motions for any operator itself. And we can find these equations of motions for quantum mechanical operators, and they often have a similarity to the classical equations. For example, a precision in a magnetic field or the classical harmonic oscillators. And here below are again the equations of motions depicted. And with this, I thanks for your active interplay with my presentation. And are there any more questions?
Very good. Thank you, Max. Then
Yeah, with this, I
please,
will stop.
please will go online.
Good morning, everyone. My name is Christo, and I'm going to be refreshing also quantum mechanics. Yuli, can I just ask you how much time is left for me?
All right, basically till 10:30, you may speak.
Okay. Okay, so let's start. Here's the outline of my presentation. First, we're going to refresh time-independent non-degenerate perturbation theory. And by that, I mean, we're just going to look at the equations. We're not going to rederive the form of equations for perturbation theory. Later on, we're going to look at the quartic perturbation of the harmonic oscillator in much detail. So as you can see, we're going to look at the first order correction to the energies by doing an integral evaluation, a second order correction to the energy using another method, evaluating operators. And then finally, we're going to look at first order correction to the eigenstates. As a lot of you asked for homework or exercises you can do meanwhile, at the end, I'm going to give you a very somehow simple example of how we can practice perturbation theory. So let's begin. What we have in, so it's time-independent and non-degenerate perturbation theory. And by non-degenerate, we mean that the eigenvalues are not repeated. So what we have is a Hamiltonian, which we write H. Let me just, okay. We have a Hamiltonian H0 for which we know the eigenvalues and the eigenstates, or the eigengets, eigenvectors. And we add a small perturbation V with a coefficient lambda that compares H0 to V. Okay. As you have seen, I hope you have seen this already in the lecture of what is the correction to the energy levels. So let me first explain the notation. Here we have the energy of the, so the corrected energy of the state n. Here, no, the yellow is not a good color. So of the state n, which is equal to the state, the energy of the state n without the perturbation. So 0 here, which I might have omitted at some places, but I will bear in mind to say it every time. 0 here denotes the eigenvalues of the unperturbed Hamiltonian, H0. And we see here the first correction that comes with the term lambda. And what we have here is the expectation value of the state n, the expectation value of the perturbation V with respect to the state n of the non-perturbed Hamiltonian again. So those are the eigenstates, eigenfunctions of the non-perturbed Hamiltonian. Let me just find the chat if you have any questions. Why is it so difficult? Okay, I'll do it later. So that's it for now. Then we look at the second order correction. It comes with lambda squared. And what we have here is again a somehow expectation over many states. So here we have a sum. This time it's not a single term. We have a sum over all possible over all states here. And those states, again, I accentuate on this aspect, those are the states of the unperturbed Hamiltonian. And below we have the energy difference. So if we're looking for the correction to the energy of the nth correction energy, we also need some differences between energies of n and k here. Now here for the correction of the eigenstates, so we have a similar structure, but this time we have the non-perturbed eigenstate here, and with the index 0, and the first correction to this eigenstate, which is again sum over eigenstates of the unperturbed Hamiltonian weighted with different coefficients. And here you notice that those terms are somehow similar. Here we have the square and the absolute value, but the terms that we have are similar. And again, energy difference between the nth and the k energy level of the unperturbed, again, Hamiltonian. Of course, this is not the final form, so we have a series of those. There is third order, second order correction to the eigenstates, but rarely you'll be asked to do anything of higher order. Okay, so very shortly, I'm gonna talk about the harmonic oscillator, because we're gonna use this knowledge to calculate a perturbation to the harmonic oscillator. So for the harmonic oscillator, what we have is, here is the H0 on the left. We have the P operator and the X operator, both of them squared, and they come with different coefficients. Of course, I think this you know from classical mechanics or analytical mechanics, and then later from, let's go with basic quantum mechanics. One way to solve this problem is to introduce operators, A and A dagger, which we call the ladder operators, or later you'll see that those will be related to the creation and annihilation operators. Here I write them, I express X and P as a function of those A and A dagger operators, not the other way around, because we're actually going to evaluate a perturbation that depends on the position. Bear in mind here I have denoted this coefficient, this whole coefficient in front of the sum of this creation and annihilation operators as, sorry, without the square root. Let me go back if I can. Yes, without the square root. So this inside the square root I have denoted by a characteristic distance of x0. We also have, of course, the P operator. This time you see there is an I in front, and which is the difference between A dagger and A. Now those ladder operators are important because they solve the harmonic oscillator in a convenient basis. And this basis is the number states. So what we have is, if we look, for example, with this equation, we go with green again, yes, green. At this equation, we see that if the harmonic oscillator is in state n, if we apply a dagger to this state, then the harmonic oscillator goes in a higher state, n+1. And there is the respective coefficient here. You notice also that A without dagger, if it acts on the state n, it lowers the state of the harmonic oscillator. It's important to note that the lowest state is for n equal to 0. As you can see, then this term is going to be equal to 0. Here on the right, I have just took this diagram from Wikipedia to show you the wave functions of the first 7, yes, the first 8 actually, first 8 states. It's important to note that there is a certain symmetry between the states here. It's good to remember and think of symmetries when we're dealing with quantum mechanics. Sometimes they simplify the problems greatly. In this case, you can see that the even states here, E0, E2, E4, E6, well, I call them even, but they're even with respect to the change of x. Here's the x-axis, so there is a certain symmetry of this energy axis with respect to x. And now the energy of the harmonic oscillator is, I hope everyone knows this, it's h bar omega, with omega being this omega, the oscillation frequency of the harmonic oscillator, and the minimum energy is not zero. If you put n equal to 0, you still have h bar omega divided by 2. I would like to find the chat. Okay, later then. So what we will do is we will add a quartic potential. So previously we had only the H0 in this description of the quantum harmonic oscillator. Now we're going to add a small perturbation here, not that small, a small perturbation x to the power 4 to this harmonic oscillator. And here I have just traced the potential to notice what happens. You see that by adding this x to the power 4, the potential gets a little bit more narrow. Okay, and now we're going to do a simple calculation in detail. What we want to do is, if you remember the formulas before, we want to evaluate the first order correction. So the first order correction to the 0th energy, to the 0th eigenenergy. So not to all eigenenergies, but just to a single one, which is the 0th. We write, here I've omitted lambda in front, but what we need to evaluate is the 0 state of the unperturbed Hamiltonian here with respect to the perturbation as before, v, in this case, x to the power 4. In our next step, what we do is we insert identity, which consists of the following. We have the integration over dx, and this bracket notation as you saw. In our next step, this operator x to the power of 4 acts on this state, and because it is this basis representation is the eigenbasis of this operator, it will give the eigenvalue, and in this case the eigenvalue will be x to the power 4 of this operator. And now we're left with those two terms. Let me go with a different color. Maybe there is yes, now I can see the chat. So okay, the notation means the following. Again, I repeat, it means that 0 here represents the 0 eigenstate, and the power, or the upscript or subscript, I guess, should be, it tells you that this is the unperturbed eigenstate. So superscript, okay. Okay, good. Then in our next stage, we have those two terms, which is in direct notation means that those are the we have the eigenstate, which is 0, the unperturbed eigenstate of the 0th unperturbed eigenstate, which is projected into the basis of the coordinate basis, or the coordinate representation. And here I have given you the coordinate representation of this basis on the right. You will not be asked to find it. It's just here I give you the eigenfunction, or the eigenstate represented in the coordinate representation of the 0th so the zeroth unperturbed eigenstate. Again, as you can see, it's a Gaussian function. We don't have any imaginary part, or it's purely real. So we just need to square it in our next step. In this step, we take the expression, we replace it here, and we have 2. So it's the we simply square it and take the absolute value, and we obtain it's good, and we have this expression, right, by squaring it. Now in the next step, I present you a simple trick of how to evaluate those type of integrals. So what I have done is we have this x0 in denominator here, and in the exponential, and also here. So I have replaced it with alpha just because it's easier for now. So alpha will be another variable, another parameter, 1 over x0 squared, such that the integral will be the derivative of another function. Now, tell me if you don't see how exactly this is obtained. So first, we replace this expression here whenever we see x0, and then we notice that because we have x to the power 4, we don't want to evaluate this integral. We want to evaluate an integral that we know by heart. We notice that if we take the second derivative of this expression, there will be, if we take the first derivative, we'll multiply it by x squared, and then if minus x squared, and then if we take the second derivative, we'll multiply it by another minus x squared, which will result into x to the power 4. And now in the next step, we evaluate this integral. It's a Gaussian integral. I hope everyone knows how to do it. If not, it's a good way to, it's good time to remind yourself. And we simply obtain this expression, a coefficient, after integrating over x. And now what we need to do to obtain the final result is to take the second derivative, and now with respect to alpha. So we take the second derivative with respect to alpha, and here is the final result after some simplification. So the second derivative gives you 1 over alpha to the power 5 divided by 2. And then we go back from, we replace alpha with, again, the expression here, which is 1 over x squared, x0 squared. So this is one way to evaluate the first order correction to the, again, I repeat, to the 0 energy state only. And now I'm going to present you the second order perturbation. So the second order, is this for lambda? So there was a question, is this for lambda equal? No, I just omitted lambda here. Lambda is still in front because this is the first order correction. So everywhere in front there is a lambda, which notes that this is the first order correction. Okay. Then the second order correction, I write again the formula for the second order correction. So you see now, this is the energy. Okay, this is the energy of the 0th eigenstate, and this is denotes second order correction. Sorry. This 2, again, the superscript denotes that this is a second order correction. So in front of it, there is a lambda squared that I did not write here. Again, we have, I write down the formula previously and replace n with the respective the respective eigenstate or the respective index. So in the general formula, here we have k is not equal to n and 0 is n. Now what I have omitted here again is the 0. So here there is a 0 and here there is a 0. So those are the unperturbed eigenstates. We have the sum. We see that it's not wise to sum over k equal to 0 because this will result into infinity and perturbation theory fails. That means that we need to go to degenerate perturbation theory if we have same eigenvalues. So that's why this is non-degenerate perturbation theory. And here on the right, we use another somehow method or another approach to solve this by applying the operator x to the power 4 to the eigenstate 0. I have not written how exactly in detail one does that. So it's important to know that we have x to the power of 0. And if you remember, it was proportional to 1 over the square root of 2 times x0. And because it's to the power 4th, we have this coefficient in front. And then in order to apply this operator on the 0th get, we apply the A and A dagger operators. Okay, so we need to apply, here, for example, we'll have A somewhere, A dagger to the power of 4th. That will be applied to the 0 eigenstate of the unperturbed Hamiltonian in this. You will not be expected to know this relation for x to the power 4th, but you will be given, let me go back and just clarify, you will be given, for example, this relation. You will be given this relation between between x and A dagger A. And knowing that how to apply those operators here, for example, you should know how to apply those operators to number states, such as those. That's why I reminded you those relations, those equations before. So you need to expand, you take x to the power of 4th, which means this, take this to the power of 4th. Bear in mind the order of operators. So commutation or you expand this to the power of 4th, and you have a lot of terms here. Some will be, as you see, A to the power of 4th. Terms that end with A will not contribute because if A acts on a 0 state, it will give you 0. And in this way, you can find how does x to the power 4th acts on the 0 state. So this is an operator evaluation. Yeah, you will not be expected, but you should know how to apply those operators to the how to calculate properly a sum of two operators by bearing in mind the order of them, and how to apply those to eigenstates if you're given the relations. So this will be the result after some tedious calculations. You will find that if you apply the operator to the 0 eigenstate, you will couple, now you don't have only the 0 eigenstate, but you also have a sum of two other eigenstates. Sorry, here it should be 0 everywhere. Okay, two other eigenstates with some coefficients in front that will come from the fact that, I'll go back again, they will come from here, those square roots. Okay, yes, just another thing to notice is that the operator here does not couple odd states. So you see it couples only 0, it's not that it couples, but we only have 0, 2, and 4. We don't have 1 and 3. and that's because the operator is even. Okay, and if we go back now, once we know this, we go back to this sum. What else do we need? Because V here is actually equal to the perturbation. So this is x to the power 4. All right. What else do we need? We apply it to the 0 ket, and then we see that on the left, k cannot be equal to 0. So we're left only with 2 and 4. All other terms will be 0. Right? Because it's a scalar product between this and k can take any values, but we see that here we have only 2 and 4. The 0 is not allowed into the sum. And below here are the coefficients, because it's the absolute value squared. We have 24, right? It comes from this, and 4 times 18, because this one is squared. This is the coefficient. This also needs to be squared, right, from the previous expression. Here we have it to the power of 4, and then we square it with the absolute value, so it goes to the power 8. And now we need the energy differences. What are the energy differences that we need? We need the energy difference between E2 and E1, and E4, and again E1. So those two will give, let's see, so we have the coefficient here for E4, so this is the difference for E4, E1, and this is the difference for E2, E0, sorry, E4, E0, and E2, E0. And now it's just simple algebra, combining the coefficients and finding the correct expression at the end. Okay, what we can do also is to look again at first order correction. Because we have evaluated this operator, the first order correction is immediately we can apply the bra on the left of this expression. So we just apply here 0, and we obtain the first order again because we project this into the 0 eigenstate, and we see that the only term that will contribute will be this one. So we have 3, and then this one is squared. So we can again find the first order correction. And now the first order correction to the eigenstate is very easy because we have evaluated this operator x to the power 4 here. Sorry, there is no, it's not equal here. So we know, again, I write it down. I've made an error here, but what is missing is the eigenstate 0, 0. So we have seen what this expression is equal to, and we apply the same technique. What we do is we have k0. The only non-contributing terms will be the 4 and the 2. 0 is not allowed, and each one of those comes with its respective eigenstate written here, 2 and 4. And again, we need the energy differences, which we saw before, E4 minus E0, E2 minus E0 again, and their coefficients from this expression, and we can find the correction. So here again, this is the first order correction to the zeroth eigenstate. Okay, and to finish off, I'm going to give you very quickly what you can do at home is to consider the following. You can consider that there is a slight change in the elastic constant, or just a slight perturbation on the quadratic potential. So as if we change a little bit this elastic constant. Could you go back? Sorry.
Rinos, he could not. What is precisely your question? You may speak up if you wish. Ines.
I was wondering if I could see the previous slide for 1 second.
Okay.
Thank you.
Okay. So the quadratic perturbation is what you can do is yeah, just apply a small change in this elastic constant and see how everything changes. And the purpose of this is that you know what the exact solution is. The exact solution is you know the exact solution for the harmonic oscillator that you can see in every book about quantum mechanics. And then you just need to replace the oscillation frequency by the square root of 1 plus epsilon, where epsilon is the perturbation parameter. And you would obtain the exact solution. But what would be interesting is now to apply perturbation theory to an already known solution. So again, here on the left, we have perturbation theory written out. Here V00 means that it's the perturbation potential squeezed between the zero and the zero brine, zero ket, and the same formulas as before. I'm only giving you the solutions now that you can see or rewatch later. The only non-zero terms here will be V00 and V20. And if you evaluate those, you would immediately, find the correction to the eigenenergies of the zero state. So here I have subtracted the energy itself. And by applying perturbation theory, you can find the coefficient. So here it's 1/4 minus 1/16 to second order. And you can do the same for the zero eigenstate. Immediately, if you know the elements, you know that the only contribution will be from the second eigenstate, from the second eigenstate to first order correction to the eigenvector. And now you could compare that. You could compare that by doing the exact solution. So this is the exact solution now by replacing omega with omega times 1 times the square root of 1 plus epsilon. And then what you need to do is expand. If you expand to first, right, you can expand to second order and see and compare this to your perturbation theory that you found before. So here there is 1/2. If I go back, epsilon divided by 2 times 1/2, it agrees with epsilon divided by 4, and so forth. And for the eigenstate correction, it's a little bit more involved because you're going to need the wave function that I showed you before. So the wave function of the zeroth eigenstate of the unperturbed Hamiltonian. One needs to replace again omega with this expression with omega times the square root of 1 plus epsilon, and then expand here and here to first order. You would get 2 terms, and those 2 terms, the first correction expansion of this wave function will give you the first correction from perturbation theory. So with that, I think my time is up. Do you have any questions before I went too fast? So the first question is, I would repeat why there is no 6. I think Yuli will upload the video of the whole presentation so that you can pause and see the slide that you're interested in. And lambda is just a parameter. It's a small parameter that defines how H0 is related to V. So you can vary it within the small interval to see how perturbation affects the original Hamiltonian. And now just going back to the initial, why there is no, so there is a question of why there is no 6th eigenstate in the second order correction of 0 for the quartic perturbation. It's quite intuitive to see that the highest you can get, so if you have x to the power 4, the highest you can get if you expand this expression is a dagger to the power 4. You cannot get a dagger to the power 6. So if you have, it's not a definition, if you have this a dagger to the power 4, you cannot get 6 because you begin from 0. So from 0, you can apply it 4 times only. So the maximum you get is 4. It's a good way to check if your calculation was right. Yes. I have not defined it. Yes, this is just an example of what lambda can be. Just trace the potential. But yeah, you're right. So here there is no lambda. So if we have to be consistent all over the way, here there is no lambda because lambda appears in front of v. But I wrote it just as an example here. So here there is no lambda.
All right. Thank you, Christa. Thank you very much. Sorry for this delay. Sorry for that it's kind of went out of time. I just wanted to mention one question. There will be no slides. There will be only video. And not that we don't want to comply with your wishes. It has clear pedagogical purpose. If you get slides, you put it somewhere and you think you have already know the material. But this is not what we want from you. We want from you to do it yourself, to be able to do it yourself without help of any slides, just formulation of the problem and go on. A little bit refreshing of your practical skills in quantum mechanics. Thank you for staying that long. This session is over.